All right, today we're going to be doing 7.6, and hopefully 7.6, if you understood 7.5, 7.6 is really similar and use the same rules and apply them the same way, so hopefully it'll be pretty easy for you. But our objectives for today are to use the number e to write and graph exponential functions representing real-world situations, and solve equations and problems involving e or natural logarithms. So, e is like pi, it's irrational. Okay? It goes on forever and ever and doesn't repeat. E is approximately 2.7182818, and that goes on out. The natural logarithm is base e. So if we wrote this, we could go log base e, but like base 10, which was just log on our calculator, that is just ln on the calculator. So it's another one we can use the calculator for, just like we did with base 10. So again, ln for logarithm natural is log base e. Natural logarithm function, remember f of x is ln x, is the inverse of f of x equals e to the x. So if we go back, remember how we've done logarithms before. Let's say 3, 2. Then we know the base is e to the second. Let's make this an x. Equals x. So again, because the variable is not in the exponent, remember this is our exponent in exponential form, since it's not in the exponent, we can just do that on the calculator. And if we go to the calculator then, we can just go e, which is second ln, e to the second equals, so our x value in this case is 7.389, rounded off to 3 places. Okay? So again, it's just like we did with other logarithms, base 10 or any other base. Because it's ln, that would be the same as log base e of x equals 2, and we put it in the exponential form. So some examples. One thing you're going to have to do is graph it. So let's go, they're going to ask you to take and graph f of x equals e to the x plus 2. So the first thing we do is we make a table with our x. And remember, our f of x is our y values. So I'm just going to make this -3, -2, -1, 0, 1, 2, and 3. And if I plug -3 in, again, you do that on a calculator, but it's approximately 2.0, and then 2.1, and then 2.4, 3, 4.7, 9.4, and 22.1. And then I can graph that. All right. So at -3, we're at 2, and then we're at 2.1, so just barely up, and then at 2.4, and then at 0, we're at 3, and at 1, we're at 4.7, and at 2, we're at 9.4. And you can see that this graph would exponentially grow as we went. So if they give you one to graph, just make the table. get enough points so you can see what the graph's doing, and make your graph. All the other stuff except the story problems you're going to do are just like we've done with logarithms so far. All the rules still apply. So we can go through some examples. Let's say we have ln e to the negative 2t. So now we use the rule that, remember, tells us if this is the same as this, my answer is whatever the exponent is. So because this is ln, remember that's the same as log base e. Since these are the same, that would just be negative 2t. So that's using this rule. If we have e ln of t minus 1, so that would be using the rule b log base b of x. If the logarithm's in the exponent and this base is the same as that base, again, it's whatever the value is. So again, because this is e and this is log base e, since those are the same, it's just t minus 1. And then let's go e, a little bit harder, ln x. Well, now we have this number in front, but remember we have a rule that says we can move that power to the front. Well, again, we can do it the other way, so we can take this 5 and rewrite this as e ln x to the 5th, and then because these are the same bases, they cancel, and it's just x to the 5th. So our rules apply just the same as they did when we worked on the previous problems with logarithms. So other things we can do, ln 7 plus ln x equals 2. So I'm going to get this down to a single logarithm. So remember, addition becomes multiplication, so 7x. Now, just like we did before on the last assignment, we want to make sure that we know where the variable is. The variable is here in our answer when we think of exponential form. It's not in the exponent. So we want to change this to exponential form. So our base is e, our exponent is 2, and then we just divide by 7. So now we can bring up the calculator. Second, ln, so e to the second, divided by 7, and we get 1.056 if we round it off. So just round those to 3 decimal places. So addition again became multiplication. Now let's do one that's subtraction. ln 3 minus ln 2x equals 5. So remember, subtraction becomes division, so ln 3 divided by 2x equals 5. Again, our variable is in the answer, not in the exponent, so we switch it to exponential form. E to the 5th equals 3 over 2x. Now I'm going to move to solve for x. I'm going to move that to the numerator. So I'm going to multiply both sides by x. And so we get x e to the 5th equals 3 halves. I'm going to divide by e to the 5th. So that's going to move, I'm going to times it by the reciprocal over here so you can see it. So x equals 3 over 2e to the 5th power. So now we go to the calculator. 3 divided by, now I'm going to have to put this whole thing in parentheses, 2 parentheses there to close the whole thing off, and we get 0.01. So you can see the rules applied just like we did before. Now I want to look at two story problems that the book has, but first we need to look at the rules we're going to use. We have a couple rules. So, continuously compounded interest. So our formula is A equals P and then e to the RT power, where A is the total amount that you get after the interest has been accumulating, P is the principal or the starting amount, R is the annual interest rate, and T is the time in years. So if you look on page 532, example number 3, it says, what is the total amount for an investment of $1,000 invested at 5% for 10 years, compounded continuously? So it just compounds one after the other. So if we look at this, we have $1,000. That is our principal, what we're starting with. Our interest rate, annual interest rate, is 5%. And our time in years is 10 years. So we plug it into the formula. We're trying to find out what we're going to end up with. So it's 1,000. And then E. And then our rate, remember, is 5%, but we have to put that as 0.05. And then times 10. Okay? So now, because the variable is not in the exponent, we don't need logarithm, so we can just type this into the calculator. 1,000, and then second, ln, e to the 0.05 times 10, parentheses, and we get $1,648.72. So again, it's not hard. We have the formula. Take the information they give you, label it, and put it into the problem. Another type of problem you're going to work with is natural decay. And natural decay you find this a lot if paleontologists, when they try and figure out how old bones are, they can use carbon dating to do that. And so this is an example of this. So NT is the amount remaining. NO is the initial amount. K is the decay constant. What's the constant rate it's decaying at? And T is in time. You also see this with something that is radioactive. It gets less and less powerful each year. And so again, there's a story problem on this on the top of page 533, and it says a paleontologist uncovers a fossil of a saber-toothed cat in California. He analyzes the fossil and concludes that the specimen contains 15% of its original carbon-14. Carbon-14 has a half-life of 5,730 years. Use carbon-14 dating to determine the age of the fossil. So, from what we know, they told us that it's 15% of what it originally was. Okay. They also told us that the half-life is 5,730. Yes, 5,730 years. Okay? So if we plug that into the formula, the thing is we don't know how much is remaining and we don't know the initial amount, but we do know the half-life. And so whatever it started at, you can make that, you can make NO 100, and then NT, the half-life, would be 50. But since we might as well make it as small as we can, let's start with our NO being 1, because when I put these into the formula and I divide 50 by 100, I'm going to get a half anyway. So I'm just going to say that we're starting, our initial amount is going to be 1. And so we know the half-life, when half of that takes place, our NT, 1/2. Okay? So if we plug it in the formula, 1/2 equals 1 E, and we don't know this K, that decay constant, so that's what we have to find out first. So I'm going to go negative K, but we do know how long the half-life is, 5,730 years. Okay? Now remember, our variable is in the exponent. When the variable is in the exponent, we have to use logarithms. Since it's base E, we're going to use ln. So all we do on this is we're going to go ln to both sides. So I do ln 1/2 equals, now this 1 we can just forget about, because 1 times whatever that is will be the same thing. Now if we use our rules, this, we can do that on the calculator, but I'm going to wait on that. The ln, remember that's base E, so these cancel, equals negative 5,730K. And so now I just divide by negative 5,730 to both sides. And we can now go to the calculator. So ln ln 1 divided by 2, you could put 0.5 also, divided by negative 5,730, and we get 1.209, and it says e to the negative 4th power. Remember that's exponential, so we move the decimal 4 places to the left. So our k is 0.00012. Okay? We round that off. So we now have our constant. So now we can go back to the problem, and we know that it's 15% of the original. So the easy way to do that, remember that's 15 out of 100. So you can pick any number you want, but again, I'm just going to say it's 100, the starting point, and that means 15% of that would be, we'd be at 15, equals E. We now know what K is, so 0.00012, and now we're going to find the time. Okay? So we divide by 100, 0.15, e to the negative 0.00012. Our variable's in the exponent, so we have to use logarithms. So we're just going to do ln 0.15 equals ln e to the negative 0.00012t. So again, I'm going to leave this way for right now. ln 0.15 equals the ln and the e, because it's base E, cancels, so we get negative 0.0012. And divide by negative 0.00012. And now we go to the calculator. And we go ln 0.15, close parentheses, divided by negative 0.00012, and we get 15,809.333. So they now know that that saber-toothed cat that they found the bones for would have been alive 15,809 years ago. So it gives you a way to calculate, when they find bones, how old those bones are. So you can see most of the work is the exact same as what we've been doing. We're just doing natural logs instead of log base 10 like we did on the last assignment. And so your assignment for today, for section 7.6, is page 534, numbers 16 to 22 all, and 30 to 36.